we have 5 different forces. The force from the ground, Fs max, the weight of the person, the weight of the ladder, and the force from the wall. So we need to think about 5 different torques. The total torque will be the torque from the ground, the torque from the force from the ground, essentially, the torque from the friction, the torque from the ladder, the weight of the ladder, the torque from the person, and the torque from the wall, the torque from the force from the wall. Choosing our origin at the ground means the torque from the ground will be 0, and the torque from the friction will be 0. So this term is 0, and this term is 0. What is the torque from the ladder, the weight of the ladder? So here's the weight of the ladder. What is R for the weight of the ladder? What is the distance from the origin to the point where the force is applied? Well, where does the weight of the ladder act? It acts at the center of the ladder. How far is the center of the ladder from the ground? The ladder has a length of 3 meters. So R for the weight of the ladder, 1.50 meters. 1.50 meters. What is the weight of the ladder? We already figured that out, 98 newtons. Times sine of, what's the angle? Let's be very, very careful. Here's the weight of the ladder. Here is R. Here's R. Here's the weight of the ladder. We want to find the angle between them. How do we find the angle between them? Tail to tail. We'll bring the weight of the ladder down here. We want the angle between those. Well, what's that? Notice that the ladder to the ground is 50 degrees. So what's the angle between the R and F? It's 50 plus 90. It's 140 degrees. The angle between R and F, which is straight down. I'll draw that in here. Here's the force. We want that angle, which is 50 plus 90 degrees. 140 degrees. Sine 140 degrees. Very good. That was a little tricky. You might want to go over that again if you are a little bit unsure about that. That force is going around clockwise, which makes that a negative torque. Very good. What about the torque due to the weight of the person? What's R for the weight of the person? Well, that distance is D. That's what we're looking for. So we have D times the force due to the weight of the person, which is the weight 784 newtons. 784 newtons. Sine of what's that angle? What's the angle between R and F for the weight of the person? Well, that's going to be the same as for the weight of the ladder. So bringing this down again, it's going to be that same angle, 90 plus 50 degrees, 140 degrees. Sine 140 degrees. Say 140.0. Again, that torque is in the clockwise direction, the weight of the person going down this way. So that's going to be a negative torque. Again. Finally, what's the torque due to the force from the ladder? What is R for the force from the ladder? That's going to be the entire length of the ladder, which is 3 meters. 3 meters. What is the force? Well, we already calculated that earlier, 132 newtons. So the force from the wall, 132 newtons. Now what is theta for that force? Here's the force. And R, again, is going up the ladder that way. Let's put them tail to tail. We'll bring this one down here. And we want the angle from the ladder to this direction. What's that angle? Our diagram is getting very messy. I hope you can figure this out. So we're looking for the angle between that direction and that direction. What's that? Well, if this angle is 50 degrees, this angle must be what? 180 minus 50 degrees. These can be a little bit tricky sometimes. 180 minus 50 degrees. In other words, what? 130 degrees. So this is 130 degrees. Those are a little tricky sometimes. This force is in the counterclockwise direction, so So this is a positive torque. And that's all of them. Those are all the torques. Adding them all together, they must equal what? They have to equal 0. Multiplying out this term and combining them, we get 209 Newton meters. So try that. Multiply this out and this out. Combine those, we get 209. Multiplying these out, we get minus 504 newtons times D. Bring this over here, divide by the 504, and what do we get? We get D is equal to, finally, 209 Newton meters divided by 504 newtons, or D is 0.415 meters. And there is our final result. Very, very good. That was a tricky one. And as I said, it's a classic, meaning you're probably going to see it again. To recap, what did we do? We had this ladder leaning against the wall. We knew the weight of the ladder, the weight of the mass of the ladder, the mass of the person standing on it, the angle the ladder made with the ground. We went through our force equations. We looked at all the forces in the x direction. We looked at all the forces in the y direction. We knew the net force in the x had to be 0. We knew the net force in the y direction had to be 0. We set the condition that we'll assume the person has gone as far up the ladder as frictionally possible. In other words, going up the ladder increases the amount of static friction required at the bottom of the ladder. Let's assume the person has gone up so far that we have maxed out that frictional force so that F was equal to Fs max. Doing that allowed us to then, after we, that actually helped us, remember, determine that the value for the frictional force, because we knew then it had to be equal to mu s times the normal force. Then, looking at the torque equation, we stuck in everything else that we knew. The only thing we didn't know was that distance d, how far up the ladder had the person gone. And we could then solve for d. Excellent. One more thing that I'd like to go over before we finish up, and that is when I was talking about the center of an object. What do we mean by the center of an object? This is a very, very important point and can be a little bit tricky if we've got an irregular object. For a regular, very symmetric object, the center is pretty easy to find. It's the center of the object. Where's the center of the ladder? Well, the ladder, if it's 3 meters long, the center is right in the middle, 1.5 meters from the end. What if we've got a more irregular shaped object, or a bunch of scattered objects? Where's the center? The point that we will refer to is called the center of mass, the center of mass of the object. I've actually written up some extra notes. We'll go through a calculation, but I'd like you to read those extra notes, and I'm sorry, these are for my students. I've posted these extra notes on my iCollege website. For those of you watching this on YouTube, I will try and find some place where I can post these other files, and I'll let you know. I'll put some attachment when I can do that, so if you want to read these too. But for those of you in my class, please read those notes on center of mass. It gives you a little more of an explanation as to what's the physical meaning of these equations that we'll be looking at. But let's take a look and let's stick some numbers in those. Let's imagine we've got two masses, M1 and M2. M1 is at some point on an xy plane that we will label as x1, y1. Those are the coordinates of mass M1. M2 is at the point x2, y2. We could have more masses, M3, M4, M5, at points x3, y3, x4, y4, x5, y5, etc. We could put more in, but I'll stick with 2. But I'll tell you how to change the equation if you want to. The definitions that we will use for the center of mass is then that the x-coordinate of the center of mass, I'll write this as x sub cm. This is center of mass, not centimeters. So the x-coordinate of the center of mass is then given by this equation, m1x1 plus m2x2 divided by m1 plus m2. If you had more masses like m3, m4, m5, then you just increase this in the numerator with plus m3x3 plus m4x4 plus etc., and then in the denominator plus m3 plus m4, etc. So you can extend this to more masses than just 2 if you want to. And then likewise, the position for the y center of mass is an equation very similar to the x, but you're just replacing the x's with y's. So you've got m1y1 plus m2y2 divided by m1 plus m2. And if you had more masses, you'd add in terms just like you would up here, plus m3y3 plus m4y4, etc., and increase the denominator, plus m3 plus m4, etc. Those are the definitions that we'll use for the center of mass. Let's stick some numbers in here. We'll do a very simple one, or a couple simple ones, and then look at a more general one. Let's imagine we have a mass m1 of 3 kilograms on the x-axis at the point x1 equals 5 meters. And then m2, which is also 3 kilograms, is at the point x2 equals 7 meters. Because they're both on the x-axis, the y-coordinates are 0, so everything for the y-coordinate is 0, x center of mass is 0. So we don't have to worry about that. Let's just look at the x-coordinate. What do we have? Using this equation, xcm equals m1x1 plus m2x2 over m1 plus m2. m1 is 3 kilograms, x1 is 5 meters, plus m2, which is 3 kilograms, times x2, which is 7 meters, divided by m1, which is 3 kilograms, plus m2, which is also 3 kilograms. We end up with 3 times 5, which is 15 kilogram meters, plus 3 times 7, which is 21 kilogram meters, divided by 6 kilograms. 15 plus 21 is 36 kilogram meters. 36 divided by 6 is 6 meters. The center of mass is at 6 meters. Where is that? Well, if this is 5 and that's 7, 6 meters is exactly in the middle. Well, this makes sense. We've got 2 equal masses. The center of mass is exactly the midpoint, right in the middle. The center of mass tells us where the center of the system is. And if we've got 2 equal masses, it's right in the middle, and that makes sense. Let's try something with something that's not going to be quite so simple. Now let's imagine we have a mass of m1, which is 3 kilograms, at the point x1 equals 2 meters, and m2, which is 6 kilograms, at the point x2 equals 5 meters. And again, we'll assume they're on the x-axis. All the y values are 0. What do we get for the x-coordinate of the center of mass? In this case, x center of mass will be m1, 3 kilograms, times x1, 2 meters, plus m2, 6 kilograms, times x2, 5 meters, divided by m1, 3 kilograms, plus m2, 6 kilograms. What do we get? 3 times 2 is 6 kilogram meters. 6 times 5 is 30 kilogram meters. 3 plus 6 is 9. 6 plus 30 is 36. Divided by 9 is 4. Kilogram meters divided by kilograms is meters. 4 meters. Where is our center of mass now? Well, if this is 2 and that's 5, 2, 3, 4, 5, the center of mass would be right there. It's not in the middle. Notice it is closer to the bigger mass. The larger mass pulls the center of mass over closer to it. It's no longer in the middle. It's now 1 meter from the 6 kilogram mass and 2 meters from the 3 kilogram mass. Notice the ratio of the distances corresponds to the inverse ratio of the masses. This mass is twice this one, so this distance is twice that distance. That doesn't work when you have more than 2 masses, but with just 2 masses we can see that. In other words, this mass times this distance would be the same as this mass times this distance. The center of mass is closer to the more massive object, and the amount that it's closer, the ratio of the distances, corresponds to the inverse ratio of the masses. Very, very interesting. Let's stick in just some general positions with masses. and we'll do some y values as well. Let's imagine that M1, 1 kilogram, is at the point 1 meter, 1 meter, and M2, 3 kilograms, is at the point 5 meters, 9 meters. Let's figure out what the center of mass is in this case. We have XCM will be M1, 1 kilogram, times X1, 1 meter, plus M2, 3 kilograms, times X2, 5 meters, plus O over M1 plus M2, 1 kilogram, plus 3 kilograms, which gives us 1 times 1 is 1 kilogram meter, 3 times 5 is 15 kilogram meters, 1 plus 3 is 4. So we have 1 plus 15, which is 16 kilogram meters, divided by 4 kilograms is 4 meters. So XCM is 4 meters. What about YCM? We have X1, Y1, which is 1 kilogram times 1 meter, plus M2, Y2, which is 3 kilograms times 9 meters, over M1 plus M2, 1 kilogram plus 3 kilograms, which leaves us with 1 times 1 is 1, 3 times 9 is 27 kilogram meters, over 1 plus 3, which is 4. 1 kilogram meter plus 27 kilogram meters is 28 kilogram meters, divided by 4 kilograms is 28 divided by 4 is 7. 7 meters. Where is our center of mass? Our center of mass is then at the point 4 meters, 7 meters. Where's that? 4 meters, 1, 2, 3, 4, 7 meters, 1, 2, 3, 4, 5, 6, 7. It's right about there. Right there. Let's notice a couple things. First, the center of mass, and if I drew this as carefully as possible, if you were to do this on a piece of graph paper, you would notice that center of mass is on a line between the two, connecting the two. That makes sense. We would expect the center of mass to certainly be somewhere along a line connecting the two. Also, notice this is the point 4 meters, 7 meters. If you actually determine what's the distance from 4 meters, 7 meters to 5 meters, 9 meters, and the distance from 1 meter to 4 meters, 7 meters, you would find that this distance was 1/3 of that distance. So that this is 3 times this, while that mass is 3 times this one. A very similar result as what happened in just one dimension. But we've got different masses, different ratios, different points. Very, very interesting. Well, I hope you get that idea. There's some homework problems you can try. And that covers it for today. Very, very good. Next time we'll actually continue with rotational dynamics and start looking at some dynamic problems, some non-equilibrium or non-static problems. What happens when the net torque acting on something is not 0? Well, it's going to start to rotate. And we'll see what happens next time.